This is the second video in our series on topology. And in the first video, we motivated the definition of a topology by looking at the notion of an open set in the real numbers, starting with an open interval, which everyone is familiar with from like a calculus class. So today what I'd like to do is start with the idea of a topological space and look for some other examples other than the real numbers with the standard topology, which is the choice of open sets that we had in the last video. So let's recall this definition of a topological space. So a topological space is a set X. It can be any type of set. Really, it probably needs to be a non-empty set. I'll let you think about that. So it's a set X together with a collection of subsets of X. In other words, a subset of the power set. And all of these subsets in the collection are called open sets. And they satisfy three conditions. So the empty set and X are inside of this collection T. In other words, the empty set and the entire set are both open sets. And then if ui is in T for all I in an arbitrary indexing set, then the union of those ui's is also in T. But we usually say that as the arbitrary union of open sets is open. And then also the finite intersection of open sets is open. In other words, if you've got u1 up to un in T, then u1 intersect u2 all the way up intersect un is in T. And notice I'm like freely passing between saying a set is in T, which is this collection of subsets, and saying that a set is open. Because in a topological space, the definition of being open is being inside of this collection. And this collection or this definition of being open is part of the definition of a topological space. So it's not fixed to a set X. A set X may have many different topological structures on them, and we'll see that. Well, starting today, we'll see that, but that'll be something that we work with throughout this entire course. Okay, so I'd like to start off with an observation, which is like a simplification of this third condition down here, and that is the third condition, this finite intersection condition, can be replaced with a just intersection of two sets condition. In other words, if u and v are in T, then u intersect v is in T. Okay, so let's see how this goes. So what we want to do is suppose that this conditional is true and prove that this conditional, which is our third condition, is true. And we'll prove that this third condition is true by induction. So it'll be induction on n, and the n is the number of sets u1 up to un inside of T. And anytime you do an induction proof, you always need a base case, and after that base case, you need your induction step. But let's observe the base case here is n equals 1, but if you have one set, then, well, there's nothing to intersect it off, and so this is like kind of obviously true. So maybe I'll just put a check mark here to say that that's true in some sort of silly sense. And I think now is a time when we might want to look at a second base case, even though it isn't strictly necessary. Let's look at the case when we have n equals 2. So we want to suppose that u1 and u2 are open. In other words, they're in T. And then by our given condition, which is this condition up here, we know that u1 intersect u2 is open. In other words, it's in T. So the n equals 2 case pretty clearly follows from this fact that we're essentially assuming the n equals 2 case. Okay, so now let's make our induction step. So any induction step starts with an induction hypothesis. So let's suppose for some value of k bigger than or equal to 2, I'm going to do it bigger than or equal to 2 because we've checked up to n equals 2. Let's suppose that if u1 up to uk are in T, in other words, we've got k open sets, then u1 intersected up to uk is in T. In other words, the intersection of k open sets is in K. And now let's suppose we have k plus 1 open sets. So I'll write those as u1 up to uk, and then uk plus 1 are all in T. And then let's note the following. We can write u1 intersect u2, intersect all the way up to k, and intersect uk plus 1. But then what I'd like to do is take that and write it as the intersection of u1 up to uk in parentheses, and then that intersected with uk plus 1. And now let's observe that this intersection up to k is an open set. In other words, it's in T by the induction hypothesis. And then, well, if that's in T, we can think of it as a singular set. And if we're intersecting it with a singular other set, that's going to be in T from our assumption up here. So in the end, the whole thing is an element of T. In other words, the whole thing is an open set. And so what we've done is we've simplified this condition over here from an intersection of finitely many open sets being open to an intersection of two open sets being open. Now, we'll leave this as the definition, but whenever we're checking if something is a topological space or if a collection of subsets defines a topology, we'll often, or we'll almost always check just the two-set intersection condition and use this observation. Okay, so now that we've done this, let's look at some examples of different topologies on different choices of sets. Okay, so here's an example of some topological spaces. Let's start with the one that we saw last time that we built everything out of, and that would be R with the so-called standard topology. So in other words, open sets, or elements of T, are subsets satisfying the following condition. For all x in U, there exists a delta bigger than 0, so that this interval x minus delta to x plus delta is contained in U. Again, that's what we took as the definition of an open set in the real numbers, and proved some conditions about that in order to derive, or in order to axiomatize to our definition of a topological space over here. And then here's another example. Let's say we've got this set X, which has 4 elements, A, B, C, D, and we've got the following collection of subsets. So the empty set, the whole set, notice we always have to have those, and then the singleton A, the doubleton CD, and then the set with 3 elements, A, C, D. And you can easily just kind of eyeball check that it satisfies these conditions down here. Well, it kind of obviously satisfies the first, as we already said. And if you union anything in here, you end up with something back in there. And so notice A union CD is ACD, so we're good to go there. CD union ACD is ACD, again, because we've got a subset inclusion there. And then if you intersect anything in there, you're also inside there. So if we take ACD intersected with A, we get the singleton A, and so we're within the set. If we take the doubleton CD and we intersect it with the empty set, we get the empty set, which is again in this collection. So needless to say, all of these conditions over here are satisfied, meaning this forms a topological space. In other words, this T is a topology on X. Now let's look at a non-example built out of the same set. So we've got X is A, B, C, D, and then let's consider the set of subsets, the empty set X, the singleton A, the doubleton BC, and then after that, the 3-element set A, C, D. And let's observe that this is not a topology, and that's because it does not satisfy either of these two conditions that are the second two conditions. So let's look at that, and that's because A union the set containing BC, which is the set containing A, B, C, is not an element of T. So we took the union of two elements and we ended up with something that's not an element. Again, that means that this condition is not satisfied. And then there's another one that we could do. Let's look at this. Maybe BC intersected with AC, D. is pretty clearly just equal to the singleton C, but the singleton C is not an open set in this setting. And so we don't satisfy this condition either. Anyway, so that's not a topology, and that tells us that we really do have to be careful about the collection of subsets that we take. Okay, so now let's look at two kind of universal examples, kind of the largest possible topology and the smallest possible topology. And so X is any non-empty set, and let's define something called the indiscrete topology, which is the topology where as few things are open sets as possible. So we need the empty set in X to be open, but other than that, there are no other open sets. So our collection, which I'll call TI for indiscrete, is only the sets empty set and X. Now let's compare that to something called the discrete topology, which is having as many open sets as possible. So in other words, every subset is an open set. We'll call that T sub D, and if every subset is an open set, T sub D is just the set of all subsets, or the power set of X. Now you can check pretty easily that these define a topology. So notice the empty set and X are inside of this first one. If you union anything in here, well, you're going to get X if you include X. If you intersect anything in here, well, again, it's going to be inside there. There's not really anything to do to check that. There's also not much to do to check this other one as well, because, well, we know the empty set is a subset of everything, so it's in the power set. A whole set is a subset of itself, so it's in the power set. And if you union any subsets, you get a subset. If you intersect any subsets, you get a subset. So those lie in the power set as well. Okay, so now that we've got these examples, what I'd like to do is prove maybe a quick result that regards the discrete topology. So here's this nice claim regarding the discrete topology, and this can really be seen as a model for how to do some homework exercises, or just an illumination into a trick that we might use from time to time. So let's say we've got a topology T on a set X, and it satisfies the following condition. Every singleton built out of an element of X is an element of the topology. So in other words, we take an element little x from X, and we form the singleton containing little x. Then that singleton is an open set. Then if that condition is satisfied, the topology is in fact the discrete topology. But let's recall, in the discrete topology, every set is an open set. In other words, every subset of X should be inside of that collection of subsets, which we're calling T. Okay, so how might we do that? Well, it's actually very, very quick if you know the trick. And that trick has to do with the way that we can write a set A. So let's say we've got a subset A, then A can be written as follows. It's going to be the union over all A in A of the singleton containing A. But check it out. We know that the singleton containing A is most definitely in our T, and that's because, well, all singletons are inside of our T. And then after that, let's notice that this union over all A in A is an arbitrary union. But we know that the arbitrary union of open sets is open. In other words, the arbitrary union of elements of T is an element of T. So that tells us that this is inside T, but that's exactly what we needed to show. Okay, so let's move on now. So now let's look at an example of what I'll call an exotic topology on R. And in this exotic topology, the open sets are going to be the empty set, the set of all real numbers, and then this open interval from -n to n for all natural numbers n. So that gives us like a nice infinite family of open sets. So that would be like -1 to 1, -2 to 2, -3 to 3, and so on and so forth. Let's observe that all of those open sets are in fact nested inside of each other. And in fact, we could put some sort of total ordering on these open sets. Notice that we would have the empty set over on one side that's contained in the set -1 to 1, which is contained in -2 to 2, which is contained in -3 to 3, and so on and so forth, and they are all contained in R. That's kind of neither here nor there, but I think that's interesting. Okay, so now what we want to do is check that this is a topology, and we'll check that by working through these three conditions over here. So let's observe that the empty set and the set of all real numbers is in our topological space, and that's essentially by given over here. Those are said to be open sets. And now let's show that the arbitrary union of open sets is open. In other words, this condition over here. Now let's observe that we don't really need to work with the open sets R or the empty set, as that won't really add much to our argument. If one of the open sets in our collection is the empty set, then it has no effect at all. And if one of the open sets in our collection of open sets is the set of all real numbers, that means our union is just the set of all real numbers, which is clearly in T, or in other words, it's open. So all of this is to say we only really need to consider open sets of this third type from this infinite family. Okay, so let's take open sets minus ni to ni for I running through some indexing set capital I. And that indexing set, well, it could be finite or infinite. It doesn't really matter. Okay, and now let's maybe observe the following. If we take the union over all I in I of minus ni to ni, we're going to get one of two possibilities. Let's observe that we're going to get the interval which starts at minus the maximum of all in I and ends at the maximum of all in I if this maximum exists. So in other words, if from this collection there is a largest in I, then when you take their union, you're just going to land there. And that's by that containment over there. I think that's pretty clear. But what if no max exists? Well, if no maximum exists, the union here is pretty clearly going to be all real numbers. But notice either way you look at that, your union will be in T. In other words, this union will be an open set. Okay, good. So now let's maybe do this second thing down here, which is to look at the finite intersections. And so just like with the arbitrary unions, we might as well not consider sets that are either the empty set or the real numbers in our intersection for the same kind of reason. It doesn't really add much. If one of the sets is the empty set, when we take the intersection, we land on the empty set, which is open. If one of the sets is all real numbers, if we take the intersection with that, it has no effect. So now let's maybe take finitely many sets of the other type. So let's also maybe simplify that. Instead of taking finitely many of the other type, what we'll do is take only two based off of the observation that intersection of 2 implies an intersection of any finite number. So let's take minus m to m and minus n to n, which are both elements of T. They are both open sets in our topology up here. And then without loss of generality, let's maybe suppose that m is bigger than or equal to n. You know, one of those is going to be bigger than or equal to the other, so we might as well order them in this way. And now let's note the following, and that is the minus m to m intersected with minus n to n is most definitely going to be minus n to n, which is back within our topology. And that's because, well, let's look at a little example here just to really drive it home. If we take the interval from minus 3 to 3 and intersect it with the interval from minus 2 to 2, we pretty clearly get the interval from minus 2 to 2. Again, because of that inclusion over there. Okay, so what did we just show? Well, arbitrary unions of open sets are open in this topology, and the intersection of two open sets is open, which by our previous observation implies that the intersection of n open sets is also open. Okay, so now let's look at another example of, in this case, a topology on the positive integers. So now let's look at this thing called the initial segment topology on the natural numbers. And in this case, the open sets, in other words, the elements of T, are going to be the empty set, the natural numbers. We always need those. And then this set containing 1, 2, 3, all the way up to n. So those are our three families of open sets, if you will. And so now we want to check these conditions are satisfied, and thus this is really a topology on n. So let's observe that the empty set and all of n are definitely in this topology just by our definition up here. And now let's show that the arbitrary union of open sets is open. Okay, so let's do this. So let's take ui to be equal to the set 1, 2, 3, ending at n sub I, and that's going to be for some n sub I in capital N, or in the natural numbers n, and this is going to be for some I in the indexing set. Okay, so that's going to be our collection of open sets. And now let's look at that union. So if we take the union over all I in the indexing set of u sub I, well, we're going to get two possibilities. So the first possibility is we get the set 1, 2, 3 ending at the maximum of all of these ni's if the maximum exists. So there are two possibilities. If we look at all of these ni's and take their maximum, it could exist or it may not exist. Those are the only two possibilities. If it does exist, then when we take the union, we clearly get this finite set that ends at that maximum. If there is no maximum, then, well, we're pretty clearly going to get the entire natural numbers when we take this union. So we'll just write n there. And that's going to be otherwise. In other words, it's going to be n if there is no such maximum. But now let's observe in both of these cases, you are an open set. So in both of those cases, you are in our set T, our collection of open sets. Okay, so now we're going to show that the intersection of finitely many open sets is open, but by our observation, we only need to show that the intersection of two open sets is open. So let's maybe suppose that we've got an ordering m less than n, and note that if we take the intersection of the set 1, 2 up to m with the set 1, 2 up to n, then, well, we're going to stop at the smaller place. So in other words, we're going to get the set 1, 2 up to m, which is in our topology. So we took the intersection of two open sets and we ended up with an open set. And, well, that implies by our observation that if we did that for finitely many open sets, we would get an open set. I guess I should say in both of these cases, I'm not using as my open sets the set containing nothing, in other words, the empty set, or the set containing everything, in other words, the set of all natural numbers, because that doesn't add any interesting calculations, just like it didn't in our previous example. Okay, so now that we've got some ideas of different topologies on different sets, I want to look at the notion of a closed set. Okay, so now that we hopefully have a good idea of what an open set is and how it depends on the topology that we're putting on a set, let's look at the notion of a closed set, which can also be developed in the same way that we developed the notion of an open set by starting with a closed interval. That's being said, that's not how we'll do it for a general topological space. And I think to do that again would not really be worth it. So how do we define the notion of a closed set in an arbitrary topological space? Well, here it is. So if we've got a topology T on any non-empty set X, we say that a subset A of X is closed exactly when its complement in X is open. In other words, X set minus A is in T. Okay, so complements of open sets are closed sets. And likewise, it's easy to show that complements of closed sets are open sets. So let's get some sort of good feel for what closed sets look like in the standard topology on R and what some not closed sets are in the standard topology on R. And so in the standard topology on R, the empty set and all of R are in fact closed sets. And that's because if you take R and you do set minus the empty set, you pretty clearly get R. You're just subtracting away nothing, and R itself is open. Okay, so what we just showed here is that the empty set is closed because its complement is open. And then likewise, we can do the set of all real numbers set minus the set of all real numbers, which is the empty set, which is an open set, so it's in the topology. But we just showed that the complement of R is an open set, meaning that R is closed. And so that means that, well, the empty set and all of R, they are called clopen sometimes. They're both closed and opened. Okay, so now let's look at the integers. So let's look at the complement of the integers in the real numbers and observe that we can write that as follows. So it's going to be this union of a bunch of intervals. And so perhaps we'll just write some of them down. So -1 to 0, union 0 to 1, union 1 to 2, and so on and so forth. So notice it's just the union of a bunch of intervals that have endpoints that are integers, but they don't contain any of the integers. So notice that that's an arbitrary union of open sets, meaning it is open, meaning it's in T. So that means that the complement of the integers is open, meaning the integers themselves make a closed set. Okay, so now what about this closed interval? So if this closed interval is not closed, then we didn't really pick the right definition. But let's look at this. If we take R set minus a b, what we'll get is the following. We'll get the interval -infinity to a, not including a, union the interval from b to infinity, not including b. And well, let's maybe draw why that's the case. So let's draw our original set, which is the set from a to b, not including a and not including b. And let's observe that if we instead just shade everything that's not shaded above, then we cannot shade A, but we shade everything to the left. We cannot shade B, but we shade everything to the right. So that's a little picture of how we take that complement. But now let's notice the complement of the closed interval AB is an open set because it's the union of two open sets. But since its complement is an open set, its original set is a closed set. And then, well, there are some other kind of similar examples like this closed interval a to infinity, and then the closed interval -infinity to b, if you will. But maybe I won't write those down. I'll let you think about those on your own. Okay, so, well, we just found some examples of closed sets, and we saw one class of examples up here of sets that were both open and closed. Now, are there sets that are neither open nor closed? Well, in fact, there are. And we'll see that in this next example. We won't see it right away, but let's look at the following sets which we will show are not closed. So this open interval from A to B is not closed in the standard topology. And that's because if you take its complement, R set minus A, you're going to get the interval -infinity to A, including A, union the interval from b to infinity, including b. But as we see, this thing over here on the right is not open. So if the complement is not open, then our original set is not closed. Now, what about the rational numbers? I'm not going to write anything down about this, but if you take the complement of the rational numbers, you get the irrational numbers. But you can show that the irrational numbers are not an open set using a fairly similar strategy to the way that we showed that the rational numbers were not an open set in the last video. Now, what about this last one over here, the interval from A to B, including A but not including B? So this was not open, I think you probably recall that, but if you take its complement, R set minus AB, what you get is the interval from -infinity to A, not including A, union the interval from b to infinity, but we do include b. But notice the right-hand side there is not an open set. And well, you can check that it's not an open set using the same strategy that we did last time with this point B over here. That's kind of what makes it not open. But if that complement is not open, that means the original set is not closed. So check it out. We've found some examples of things that are both open and closed, and some things that are neither open nor closed. And in addition, some things that were open but not closed, and some things that were closed but not open. So let's maybe look at a brief summary of types of sets of real numbers. So here's a partial summary of the types of sets you might see in the standard topology on R. So in our big orange box, I've got the power set of R, in other words, the set of all subsets. And then in my green circular shape, I have the open sets, and in the blue circular shape, I have the closed sets. And well, let's observe that earlier in the last board, in fact, we saw that the set of all real numbers and then the empty set, they were both open or closed. So we would put them there in the intersection. And then some examples of open sets were, for example, the open interval from A to B, the open interval from A to infinity, where really A and B are any real numbers. And then maybe the open interval from minus infinity to B. Those were examples of open sets. And then, well, we could have some others too, like maybe the interval from minus 3 to 2 unioned with the interval from 5 to 10. So the union of two open intervals, that was an open set. And then what about some closed sets that were not open sets? Well, those would lie out here. And that would be, for instance, maybe the closed interval A to B, the closed interval A to infinity, maybe the closed interval minus infinity to B. Those were some examples we saw. You could also, for instance, have the integers. We argued why that formed a closed set. You could also have the singleton x for any real number x. That is, in fact, a closed set as well. And then, well, we saw some things that were not open nor closed. And some examples of those were the rational numbers, and then perhaps the half open interval A to B, including A but not B. And then we could have maybe the half open interval A to B, including B but not A. And then, of course, there are more examples of all of these types. Well, sneakily, perhaps there's no more example that are both open and closed, but we'll get to that later. But there are most definitely more examples of open sets and more examples of closed sets than we have here on the board, and more examples of neither sets. But I think maybe to build an intuition, this is a good place to start about thinking of types of subsets of real numbers in these categories. Okay, so now what I'd like to do is prove a kind of a standard result regarding closed sets. So let's recall in the definition of a topology, the arbitrary union of open sets is open and the finite intersection of open sets is open. But in fact, with closed sets, you get a dual result. And that is the arbitrary intersection of closed sets is a closed set, and the finite union of closed sets is a closed set. And these will follow really quickly from our condition on open sets that is within the definition of a topological space. Okay, so let's suppose throughout that T is a topology on a set X. Okay, and then let's suppose that A sub I, which is a subset of X, are closed for all I from some indexing set I. In other words, we've got this arbitrary collection of closed sets. But what does that mean? That means that U sub I, which I will define as X minus A sub I, are all open. In other words, they're all in T. And this is going to be true, again, for all I in I. That's because we're taking the complement of closed sets and forming an open set. That's the definition of a closed set over here. And now all of this will be finished off very, very quickly with the following claim, which you may have proven before in like a proofwriting class. And that is if we take X and we take the set difference with the intersection of all I in I of A sub I, we're going to get the union over all I and I of U sub I, which is in T. But then that means that the complement of this intersection is an open set, meaning that the intersection is a closed set. But we do have to prove this claim to really finish the whole thing off. Okay, so we can actually prove this claim by set inclusion, but we can do it really all at once using if and only if statements. So let's observe that if we take x in the set x minus the intersection over all I in I of ai, then that's equivalent, or that's if and only if x is not in the intersection over all I in I of ai. That's just the definition of being inside the complement of a set, is that you are not inside the set you're being complemented. Okay, but what does it mean to not be in an intersection? Well, you're not in an intersection if there exists some j from the indexing set such that x is not in a sub j. But let's recall that a sub j is x minus u sub j. And that's just by flipping this around right here. But if x is not in x minus u sub j, that means that x is in u sub j. Okay, but then if x is in u sub j, then that tells us that x is in the union over all I in I of u sub I. It's in at least one of them, meaning it's in the union of them. But that's exactly where we needed to end up. We showed that x is in this left-hand side if and only if it's in the right-hand side. And just to reiterate, we showed that the complement of this intersection is an open set, but being the complement of an open set means that you are in fact a closed set. So this intersection is a closed set. Okay, so I'm gonna maybe leave this other condition, the finite union of closed is closed, as a homework exercise. But before I show you the rest of the homework exercises, I want to look at an example showing that we really do need this condition finite union. So now we're going to show that an infinite union of closed sets may in fact not be a closed set. And we're working here with the standard topology on R. And it's all going to be built out of the following claim, and that's the union as n goes from 1 to infinity of the closed interval 1 over n to 1 is equal to the half open interval from 0 to 1. Now let's observe that all of these closed intervals are closed sets, but the right-hand side is not a closed set. So we've got this setup where an infinite union of closed sets is not closed. And how can we prove this? Well, we'll prove it with double set conclusion, but let's observe that this union being a subset of the interval from 0 to 1, that's a clear result. So we'll show that the other containment holds. Okay, so let's suppose we've got a number x on the interval from 0 to 1. So not including 0, but yes, it could include 1. But that means that 1 over x is bigger than or equal to 1. Well, I think that's pretty clear because x is between 0 and 1. If you take the reciprocal, you're going to land with something bigger than or equal to 1. Okay, so now let's find some natural number which I'll call capital N, such that capital N is in fact bigger than or equal to 1 over x. This is by the so-called Archimedean principle. We can always find a natural number larger than any given real number. Our given real number here is 1 over x. But now if we take the reciprocal here, what we see is that 1 over n is less than or equal to x, which in turn is less than or equal to 1. But that means that x is on the closed interval from 1 over capital N to 1. But if it's on one of the closed intervals like this, then that means it's in the union for sure. So in other words, x is in the union as n goes from 1 to infinity of our closed interval 1 over n to n. But that's exactly what we needed to do to show the other containment. So that means that these two sets are equal, and we have our example of why we need to only have the word finite when taking the union of closed sets in that previous result. Okay, now I'm going to leave you with some exercises. So here's some exercises based on what we did today. So the first is take any non-empty set X and show that this object or this collection of subsets defines a topology. And what's this collection of subsets? Well, it's going to be all subsets U of X where the complement of U is finite or the complement of U is all of X. So to show this is a topology, you have to show it satisfies those three conditions in our definition. Then secondly, let's suppose that we've got a topology on R where the open sets are the empty set R and then open intervals from minus little r to little r where R is rational. And those are the only types of open sets. And now, I guess what we should say is, does that define a topology on R? I guess I misused the name open set if it in fact does not define a topology. So decide, does that define a topology or not? And then next, let's show that the finite union of closed sets is closed, and this is in an arbitrary topological space. So that fills in the proof of that proposition that we wrote on the board. And then finally, let's describe all possible topologies on the three-element set A, B, C. And so that means you need to find all possible collections of subsets that satisfy those three conditions that define a topology. And that's a good place to stop.